Okay, so we're going to take a look at exercise 4 on page 69 of the workbook. And this is an exercise that really tests to see if we understand the connection between a function and its derivative. Okay, if we just kind of read the beginning of this question together, they're giving us the graph of the derivative of a function, f prime of x, and they're asking us a bunch of questions about the original function. And it's going to be very important through this whole example to remember that the graph we're given is the derivative and not the original function. Okay, so for example, in part A, they are asking us, what are the critical points of f, the original function? Okay, so we have to ask ourselves first, what is a critical point of a function? Well, that's a place where the derivative of the function is equal to 0. Okay, so we're looking at the graph that we're given and just trying to pick out the places where the derivative is 0. And I can see 3 points where that's true. 1, 3, and 5, just those places where we touch or cross the x-axis. So those 3 numbers must be the critical points of our original function f. And just to remind you, those are places where the derivative is equal to 0, just where our graph crosses through the x-axis. Okay, moving on. Next question they ask us is where the original function is increasing or decreasing. And here, if we just focus on the increasing part of this for a minute, it's helpful to remember that a function is increasing where its derivative is positive. Okay, we are given a graph of the derivative, so we're looking for where that graph is above the x-axis. That would be where it's positive. Okay, I'm going to go over to the graph and just highlight the part of the graph that's above the x-axis. Notice that that goes with an interval of x values from 0 to 1. Okay, and so that must be where our function is increasing. Okay, and we identified that interval just by noticing that the graph of our derivative was above the x-axis on that interval. Okay, so to answer the question of where f is decreasing, it's just the other way around. Now, we're looking for where the derivative is negative, okay, and that's where the graph of the derivative is below the x-axis. Okay, and I'm just going to highlight those parts of the graph. So there's a little stretch from 1 to 3 and another stretch from 3 to 5. Those are the places where the derivative is negative, and so those are the places where f is decreasing. Okay, from 1 to 3, and again from 3 to 5. Okay, because the first derivative is below the x-axis there. Okay. And then we move on to part C, and this asks us, where does the original function have a local maximum? Okay, how do we answer a question like that if all we have is a graph of the derivative? Okay, well, let's think about that graphically for a minute. Okay, I'm just going to draw kind of a little snippet of a local maximum of f. Okay, it's going to look like this, the top of a peak. And what I'd like to notice is how the derivative is behaving on both sides of that peak. Notice that to the left of the peak we're going up, so we're getting a positive derivative, and to the right of the peak we're going down, we get a negative derivative. So we're looking for a place where the derivative is positive on one side and negative on the other. Are there any points on our graph that look like that? Okay, well, I see one right here at the number 1. Notice that our derivative is above the x-axis to the left of 1 and below it to the right of 1. That's giving us a positive slope to the left and a negative slope to the right. So our original function should have a maximum there. All right, so our answer is yes at x equals 1. And our reason, again, is just the behavior of the derivative. F prime of x changes from positive above the x-axis to negative below the x-axis there. Okay, so answering part D is going to be similar. Okay, a local minimum would be a place where it's the other way around, where the derivative graph goes from negative to positive, in other words, below the x-axis to above it. And so we would go back up to our graph and ask, are there any points like that? Are there any places where the derivative goes from below to above the x-axis? Well, I don't see any. What do you think? I don't see any places where the graph goes from below to above. And so it looks like our answer is no. There are no places where f has a local minimum. Okay, and our reason will be our derivative graph never changes from negative to positive. Okay, and finally, we come to probably the most challenging of all of these questions, part E. Here, they're asking us about concavity. I'm going to scroll up just a little bit here. Okay, and what's hard about this question, I think, or what makes it challenging, is concavity is usually about the second derivative, okay, determining where it's positive or negative, and we're not given a graph of the second derivative. We're given a graph of the first derivative. So how do we answer a question like this if all we have is a graph of the first derivative? Okay, well, one way would be to think about connections between the second and the first derivative. So let's start just with the concave up part of this question. Remind ourselves that concave up, a function will be concave up when its second derivative is positive. If you go back a ways in the course, we talked about how the second derivative is positive when the first derivative is increasing. Okay, so we can answer this question of where f is concave up by asking, where is the derivative graph an increasing function? Okay, well, let's jump back up to our graph at the top. Okay, I'm going to get rid of some of the marks that we made on the graph earlier. And we're asking the question, where would that first derivative be an increasing function? I'm going to change colors on you here. And I see a couple of intervals where that happens. So one from 2 to 3 here, and another from 4 to 5. We're going up on both of those intervals. And so those should be intervals where our original function is concave up. Okay, let's scroll down and just write down those two answers that we got. So f is concave up on 2 to 3 and again from 4 to 5. We got those intervals again by looking at where f prime is increasing. All right, and to determine where f is concave down, it's just the other way around. Now we're looking for where the first derivative graph is decreasing. Okay, so let's go back to our graph for just a minute. Okay, and it's going to be decreasing on the other intervals. Okay, so from here to here, which looks like about from x equals 0 to 2, and again from x equals 3 to 4. Those are the intervals where our original function should be concave down. Okay, and just as a last reminder, we identified those by noticing that that's where the derivative graph is decreasing.